Hello everybody, today I'm gonna tell you how you can solve the simple harmonic motion problems easily. First, let's talk about oscillation. This is a wave which is oscillating. So it has amplitude, period, and frequency. Amplitude is the maximum displacement from the equilibrium position. From here, which is in equilibrium position, to the maximum displacement. This is an amplitude. And amplitude is same for from here to here, from here to here, from here to here is the same. So the unit of the amplitude is meter. Period t, which the unit of the period is seconds. From here to here, it's 1 period. From here to here, it's 1 period. Frequency is 1 over t, and the unit of the frequency is hertz. We talk about today. We're gonna talk about angular. We are gonna talk about simple harmonic motion. So the angular frequency for simple harmonic motion is radical k over m. We are gonna talk about this when we want to solve the problems. K is a spring constant. M is a mass of the m is a mass and k is a spring constant. This is just for simple harmonic motion. For other motions, each one has different angular frequency. For this one, it's radical k over m. Okay, now for frequencies, when we talk about the high and lower frequency, when the period is shorter, like in second oscillation, this is the second oscillation, this is the first oscillation. In second oscillation, the period is shorter than the first oscillation. T1 is greater than T2. So because T1 is greater than T2, so F1 is less than F2. So when the oscillation has longer period, so it has lower frequency. So this one, the second oscillation has shorter period, so it has a higher frequency, and the first oscillation has lower frequency because it has longer period. Okay, now let's talk about simple harmonic motion, which for simple harmonic motion we use the angular frequency equals by radical k over m. Let's talk about the simple harmonic motion. For simple harmonic motions, the easiest problem for simple harmonic motion is the mass spring system problems. For mass spring system problems, which like spring and the mass which is attached with a spring. So there's a mass spring system which we use Hooke's law, and Hooke's law is F of the spring, force of the spring equals by negative kx. K is a spring constant, and x is that how much we stretched or compressed the spring. And the unit of the k, which is constant, spring constant, is n over m. So now let's solve the problem. Okay. So this is a simple harmonic motion problem, and the simplest question, which is spring mass system. So this is a spring mass system. Here the x equals by 0. When x equals by 0, the mass is located at x equals by 0. So this is in the equilibrium position. When x is 0, the mass is located at x equals by 0. This is an equilibrium position when the force of the spring is 0. In this case, the first one, so when we stretch the spring, the force of the spring goes to the left, and when we stretch the spring. Now we stretch the spring, so x is the mass is located no more and x equals by 0. And then when we compress the spring, the force of the spring goes to the right. And when we compress the spring, the force of the spring is positive. When we stretch the spring, the force of the spring is negative. And this position is equilibrium position when mass is located at x equals by 0. So now what's the question? So the question said, in an experimental setup, a 5 kilogram mass is attached to a spring so that it oscillates without friction about the point x equals by 0. the equilibrium position of the spring. The mass oscillates back and forth x equals by 4 meter and x equals by negative 4 meter. The spring constant is 125 N over m. At time t equals by 0 seconds, the mass is located at x equals by 2 meter and is moving in the position in the positive direction. Okay, so this is information which is given. Now, the part A said, what's the amplitude of this oscillation? So in the question it said the mass oscillates back and forth from x equals by 4 meter to x equals by negative 4. So the amplitude of this oscillation is 4 meter because we can stretch or compress at maximum and minimum of 4 meter and negative 4 meters. So the 4 is the amplitude of this oscillation. Part B said, what's the angular frequency of this motion? So the angular frequency of simple harmonic motion is omega equals by radical k over m. K is a spring constant and m is a mass. So k is a spring constant which is given 125 N over m. We put that there for k, and m is a mass which is a 5 kilogram mass. So 125 over 5 radical 125 over 5 which is 5 rad per second. Part B said, what's the frequency cycles per second or hertz of this motion? What's the frequency of this motion? So the frequency, this is an angular frequency, this one is frequency. So the frequency, it's equals by angular frequency over 2 pi. So we have angular frequency which we found in part B. It's 5 rad per second over 2 pi. So we will got 5 over 2 pi hertz. In part D said, what's the period S of this motion? So the period of this motion, period is 1 over f. So period, it's 1 over 5 over 2 pi, which is period is 2 pi over 5 seconds. This is a period of this motion. In part E said, write down the position as a function of time x of t that describe this motion. Okay. So for simple harmonic motion, for simple harmonic motion, the position as a function of time, is equals by a cosine of omega t plus v. A is an amplitude, maximum displacement from equilibrium of the mass. Cosine of omega is angular frequency in rad per second. T is a time plus phi. Phi is a phase constant, and it means where the mass is located at t equals by 0. So where the mass is located at t equals by 0, which means when t is 0, what's the position of the mass? So we put the position of the mass, we put for t 0, and where the mass is located at t equals by 0, we put that for x, and the amplitude, and then we can get the phi, phase constant. So this is equation for position as a function of time for simple harmonic motion. Now in part E, which said write down the position as a function of time x of t that describe this motion. So we use this equation, x of t equals by a cosine of omega t plus phi. So we use that. Okay, so first we need to find phi. So for finding phi, we need to know where the mass is located when t equals by 0. So for finding phi, we should find like t is 0, and we should find when t is 0 where the mass is located, the location of it when t is 0. So we want to find this. So in the question, it said at time t equals by 0 second, the mass is located at x equals by 2 meter and is moving in the positive direction. So in this case, we know when a t is 0, the mass is located at x equals by 2 meters. So when in this case, x of 0, when t is 0, the mass is located at 2 meters. Okay, so now we can find the phi. We use our equation and we say x of 0, okay, is equals by a cosine of omega t plus phi. Now, okay, now x of 0 is 2 equals by amplitude, which we find in part A is 4 meter. So we put 4 cosine of omega angular frequency, which we also found in part B, which is 5 rad per second. And t is 0, here t is 0, and plus phi. So we can find phi, and then we found the phi. Phi is cosine inverse of 1 over 2, which is pi over 3. So we found the phi, the phase constant. Now we can solve the part, we can write the equation for in part E. We said that the position, write down the position as a function of time x of t, which is described as motion. Now we can find that. So we have x of t equals by the amplitude, which is 4, cosine of omega, which is 5, t, and then pi over 3, which we found the phase constant. In part F, so it's asked how fast is the mass initially moving at t equals by 0 seconds. So now we want to find the velocity. How we can find the velocity? So for finding the velocity, okay, so for finding the velocity is the derivative of the position. So when the position is a cosine of omega t plus phi, so we want to find the derivative of the position. So we found the derivative of the position, which is equals by velocity. The derivative of the position, it's a omega sine of omega t plus phi. So we found the velocity as a function of time. We found the derivative of position, and now it's v of t. The velocity as a function of time is amplitude times angular frequency, sine of angular frequency times t plus phi phase constant. Phase constant, which we found, it's pi over 3. Now we have that, so we can put everything there. And here said, okay, when the t equals by 0, how fast is the mass initially moving when t is 0? So we have this, so we can put everything there. So we have when t is 0, so this is 4, this one is 5, 4 meter, 5 rad per second, sine of again 5, t is 0, plus phi is pi over 3. Okay, so then we can get the velocity when v is 0. Okay, when v is 0, which we get negative 10 rad 3 meter per second. Okay. The next part G said, what's the mass's maximum speed? Now we want to find the maximum speed. So what's the maximum speed? The maximum speed okay, so the maximum speed, it's when we want to find the maximum speed. Okay, So the maximum speed okay, so Vmax, the maximum speed, is A omega. It's amplitude times the angular frequency. So the maximum speed is amplitude times angular frequency. So in part G said what's the maximum speed? Is V equals by A omega, and A is 4, omega is 5, so we get 20 meter per second. Okay. In the part H, okay. So part H said graph the position versus time over one complete cycle in the provided plot below. Okay. So this is a plot which we have. It said graph the position versus time over one complete cycle in the provided plot below. So this is a one cycle, right? One cycle, one period, one period, one cycle. Okay, so this is a position versus time. Position versus time. Now, graph the position versus time for this. So we should see what we have. So like when t is 0, in the question said, at time t equals by 0, the mass is located at x equals by 2m and is moving in the positive direction. So in our plot, it said when time is 0, x is 2. And then we can like put the other numbers for x for t, and then we can get the x. We can use our equation. We can use our equation which we have here. X of t equals by a cosine of omega t plus phi. We have phi. We have angular frequency, which is phi is pi over 3, angular frequency is 5 rad per second, and amplitude is 4 meter. So then we can, for t, we can put any numbers, and then we can get the x, the position, and then we can complete our graph here. Like we can put in our equation, we can put for t 0.5, and then we can get the we can get the position like we can write for t 0.8, and then we can find the position x, and then we can graph the position versus time like this. Okay, the last question said what's the total energy in joules of this oscillation? So for energy for simple harmonic motion, for finding the energy, we use this equation. E equals by 1/2 of K A squared. 1/2 of K A squared. K is a spring constant, it's an unit of it is N over M, which is 1/2 of 125 N over M, and A is an amplitude, which is A is amplitude, which is 4, and then we can get the E, 1/2 Ka squared, and then we can get the E in joules. Okay, so this is a one simple question from simple harmonic motion. If you have any question, you can write in comments. I'm gonna answer them, and I'm in the next video I'm gonna use another questions to let you how you can solve the simple harmonic motion easily. Thank you so much for watching this video. If you like this video, please thumbs up and subscribe this channel.